Hi, good evening. Am I audible?
Yes, sir, audible.
Audible, right? Okay. So yesterday we have done up to this. Tomorrow we will continue after this. So next, suppose you have this. Next point. Suppose you have metal ligand bond. Okay. Suppose you have metal ligand bond and you have metal metal bond. So in between these two, okay, this metal ligand and metal metal, keep in mind this metal ligand bond is always more strong or more stable than your metal metal bond. Okay, so this metal ligand will be your more strong, or I can say more stable. Fine. So suppose I have, so this is your nickel. Nickel is the metal center here. This side also you have nickel. This thing. Okay. Now suppose in presence of this R2S2 and H nu, what will happen? So if you provide energy H nu, so that means heat energy, okay, or light energy. So that time what can happen? So you can see this is your R2S2. So this is basically like your peroxide type. Okay, so peroxide means what? Peroxide means oxygen, but here you have sulfur. So in presence of H nu, what will happen? This sulfur sulfur bond will cleave. Okay, so basically you are getting what? You are getting S dot. Okay, you are getting this kind of radical, and in presence of H nu, if you see, this bond will also break. Okay, this metal metal bond will also break. Okay, so ultimately what you are getting, so you have already one cyclopentadienyl rings ligand. Here you have nickel. Okay, this side you have CO, and this is now attaching with your SR. Okay, so that is the thing you have. 2 moles of you will get of this. Okay, you can see how many electron system it is. So nickel is basically 10 electron system. From the cyclopentadienyl you will get 5 electrons. Okay, carbonyl you will get 2 electrons, and SR is donating only 1 electron. So overall you are getting 18 electron. Okay, done.
Yes, sir.
Okay, next suppose you have this thing, consider here 4, and here you have this PHCH2 MgCl. Okay, in the presence of ether. So what you will get?
Sir, 4 CL only.
Hmm. So basically, if you see, you have this zirconium chloride. This zirconium chloride. So you have this metal chlorine bond, and this is your Grignard reagent. So magnesium is positively charged, and this carbon is negatively charged. So basically, this carbon center will attack on the zirconium center, and chlorine will leave from here. So similarly, the like 4 PHCH2 minus will attack here. So what I will get? I will get Zr. Then you will have this CH2 PH whole 4. Okay, CH2 PH whole 4. Fine.
Yes, sir.
And what will be the side product? The side product will be your magnesium chloride. Side product is your magnesium chloride. So similarly, suppose you have this. This thing you have. So tell me what will be the product now. So carbon lithium bond. So lithium is metal, right? So that means lithium is positively charged, and this carbon center will be negatively charged, right? So what will
Sir.
happen? This negative charge will attack on the metal center. Chlorine will leave from here. So what I am getting? PH3P whole 2. This side you have platinum. So now see 1, 2, 3, 4. So this is basically attaching with your number 1 carbon. So 1, 2, 3. Okay, then you have 4. Now again lithium is positively charged. Okay, lithium is positively charged and this fourth carbon is negatively charged. So what will happen? This negative charge will attack on the metal center. Chlorine will leave from here. So ultimately what we are getting? We are getting this PH3P whole 2 platinum, then 1, 2, 3. Okay, so that will be the product. Clear?
Yes, sir. Yes, sir.
Clear. Suppose you have this thing PCl3, okay, phosphorus trichloride. If I react to it PHMgBr, can you tell me what will be the product?
One chlorine will leave, or the phenyl group it will attack.
Huh?
pH minus it will attack the phosphorus center. Chlorine will leave.
So basically pH minus will attack. So what you will get? You will get PPH3. Okay, if you use 3 equivalent of this phenyl magnesium bromide, you will get PPH3. Fine. Okay. Now suppose you have this. So here you have cyclopentadienyl ring. Then here you have iron center. You have two carbonyl ligand. This is attaching with one carbon center, and here you have deuterium and two methyl group you have here. Okay, two methyl group you have. Now here you have one carbocation. So phenyl. This is your triphenyl carbocation. So now tell me what will happen. So basically this is a carbocation you have. So if you have carbocation, so that means anything negatively charged species will attack this carbocation, right? Or I can say this
Yes,
carbocation,
sir.
this is a very stable carbocation, you know, because you have 3 phenyl ring. So basically this is, I can say, H minus acceptor. Okay, this carbocation is actually highly H minus acceptor. Okay, but if you have 3 phenyl rings, okay, as it has 3 phenyl rings, so this carbocation is actually hindered one. Okay, this carbocation is actually hindered, so therefore abstracts abstracts H minus abstract H minus from less hindered side. Okay, so it abstracts H minus from less hindered side. That is the thing. Okay, so if you see here, so here you have methyl group. So if you have methyl group, so basically I can show like this, that CH2 hydrogen. So what will happen, this hydrogen is releasing as H minus and it is attacking on the carbocation. Okay, this hydrogen is releasing as your H minus and it is attacking on the carbocation. And if it does, so what I am getting, draw here what you are getting. So you have iron here. Okay, 2 carbonyl group you have, carbon you have, deuterium you have, this side you have CH2 minus and here you have CH3. So what will be next?
CH2 plus, sir.
CH2, yeah, CH2 plus, sorry sir, yeah, CH2 plus, because hydrogen is releasing as H minus, so it will be your CH2 plus. Yeah, fine. Now what can happen, now see, if this bond breaks like this, okay, if this bond breaks like this, so that means what, carbon is getting negative charge and here this carbon center you have positive charge, right? So basically what we will get, we will get carbon double bond CH2, this carbon will have two groups. What are they? One is your deuterium and another is your methyl group, right? And if you see the other part, this part, so here what you have, here you have the cyclopentadienyl, you have, next you have iron center. Okay, which charge will be on iron center now?
Positive.
Positive charge. Okay, positive charge you will get, and here you are getting double bond. Now check how many electron system it is. How many electron system it is, this positively charged?
16 electrons.
16 electron. So it is your 16 electron. So what can happen? Any idea? How can you make it 18?
Mm.
You are getting these two products. How we will make you 18?
Pi donation. Double bond.
Double bond will donate the
Donating 2 electrons.
2 electron. Correct. So that is the thing. So here you have Fe. Write down the first of all this product. You have CO, right? And this side you have CH2, double bond carbon, you have deuterium, and another is, I think, methyl, right? Yeah, so you have positive charge. I am not showing the positive charge here because you can show the positive charge overall. I am showing the positive charge on iron as overall. So basically this double bond is donating the 2 pi electrons to the metal center, and that time it will become your 18 electron. Clear?
Yes, sir.
Fine. Now, next, suppose you have this.
Sir,
Ah,
uh, carbocation, why it will not obstruct the deuterium?
because hydrogen is smaller in size, na? If you compare
Hmm.
with if you compare deuterium with hydrogen, so hydrogen is smaller, so it will move faster. Okay, not deuterium. Okay, it will move faster, not deuterium.
Hydrogen is a smaller element.
Hydrogen is smaller element, na? So the speed will be high.
Bond become a strong.
Huh?
It will become a strong bond compared to deuterium.
No, no. If suppose this is your hydrogen, so this is your small, and suppose this is your carbon atom. This is your hydrogen, this is your carbon. Now, if you move to deuterium, that time deuterium is larger in size compared to hydrogen, and this is your carbon. So, if size is increasing, that time the bonding, like overlap will be high. Overlap will be higher if your size is increasing, and that means the bond will be also stronger. Bond is getting stronger if you are overlapping with similar size. Okay.
Okay, sir. Okay.
That's why the carbon hydrogen bond breaks easily, not carbon deuterium.
Okay, sir. Clear.
Fine. So suppose you have this. Now here I am using NO in presence of heat. So what will happen? First of all, check how many electron system it is and what can happen.
20 electrons.
Hmm. So 20 electrons you are using NO. So basically, if NO is substituting this other cyclopentadienyl, that time you will get 18 electron. So that is the thing. If you treat this compound with nitrosyl and heating, that time you will get 18 electron compound. Okay.
Yes, sir.
Until many doubt.
No, sir. Clear.
Clear, right? Okay, just a minute. So next, what do we have? So we have this metal carbonylates. Okay, metal carbonylates. So what do you mean by carbonylates? So yeah, let's see. So basically you will have a negative charge. So similarly, suppose in organic chemistry you have done like this. Suppose you have this CH3 C double bond OH. This is what? This is your acetic acid. In organic chemistry this is actually known as your acetic acid. Now if I have this thing CH3 C double bond O minus, this unit is actually known as your acetate. Okay, acetate. So carbonylates, so this 8 is coming basically for your negative charge. Okay, so what are the things you will have in metal carbonylates? So in metal carbonylates, first of all you need one metal center. Okay, next you need carbonyl. carbonyl ligand should be present there. Okay, and keep in mind from this 8 term you need some negative charge as well. So if you have a metal center, carbonyl is the ligand, and you have negative charge, that time you can call it metal carbonylates. Okay, metal carbonylates. So suppose you have this is in general, suppose you have metal CO whole X. Okay, now I am reacting with any alkali metal. Suppose you have one alkali metal. So alkali metal means what? They are donating electrons. Okay, so suppose you have sodium, potassium, these are the alkali metals you have, so they will donate electrons, and those electrons will be taken up by this metal center. If they abstract the electron, so that time you will get like this, M CO whole X minus. So this is actually your metal carbonylates. Okay, this is actually your metal carbonylates. Fine. So metal carbonylates mean this kind of thing. You need a metal center, you need carbonyl ligand, and if it contains negative charge, so it is your metal carbonylates. Fine, done. So now we will move to the preparation. Okay, how to prepare this kind of metal carbonylates. So give a heading, preparation. Preparation. So suppose you have this compound vanadium CO whole 6. Okay, vanadium carbonyl, vanadium CO whole 6. If I react with sodium, so what will happen? How many electron system it is?
17.
17 electron. So if sodium, in batch reduction in organic chemistry we have done, sodium did what? Sodium release one electron and it becomes sodium plus. So this electron will be taken up by vanadium also. So if vanadium taken up this single electron, now it will become vanadium CO whole 6 minus and 18 electrons. So that means this compound is not that much stable, but this carbonylate form is stable actually, because it is getting 18 electrons. Okay, now similarly suppose you have here this thing CO whole 5, then you have metal bond as well, then again you have CO whole 5. Now in presence of sodium amalgam, sodium amalgam, in presence of sodium amalgam, what will happen? This metal bond will cleave. Okay, and if metal bond is cleaving, so what I am getting? Metal CO whole 5, and you will get a negative charge here. So I am getting 2 units of this. Okay, metal CO whole 5 negative charge, and you are getting a negative charge as well. Fine. Suppose I have this kind of compound, Fe3CO whole 4. So like this, iron is there. Here you have also FeCO whole 4, and this side also you have Fe, then CO whole 4. Okay, now suppose I am treating or I am reacting this compound with sodium excess sodium I am using. So what will happen? This metal bonds will cleave. Okay, so just look at one metal center, what is happening? So you have FeCO whole 4, how much bond is breaking? 2 bonds is breaking, right? So what I will get? So FeCO whole 4 2 minus, how much metal center you have? 1 2 3, so just make it 3 unit of this FeCO whole 4 2 minus. Okay, you just check here, you will get 18 electrons. Fine. So this is how, this is your Fe3CO12. Similarly, suppose you have osmium 3CO12, and same thing I am doing. I am reacting with sodium in presence of excess sodium. So what you will get? You will get osmium CO whole 4, osmium CO whole 4 2 minus. Okay, fine. Now
2
suppose
minus how it come?
Same thing, same like this. Same thing, you just do you just replace osmium in place of iron, you will get 2 minus. This bond is breaking and this bond is breaking, so 2 minus na.
Um, okay, sir.
Each iron center is making 2 bonds, so if you break 2 bonds, what you will get? 2 minus.
Okay, sir.
Suppose you have CO2 CO whole 8, CO2 CO whole 8. So in presence of sodium amalgam, what will get? So you have 2 cobalt center, cobalt 2 cobalt, CO2 means what? You have 2 cobalt center. So if you break, so that time what you will get? You will get CO whole 4 minus, CO whole 4 minus. Okay.
Yes, sir.
Suppose you have this, you have iron, this is your bridging CO you have. Here also you have one iron center. This side also I have one bridging CO. Here you have iron iron bond. Okay, CO is there. This side I have the cyclopentadienyl ring. Here also I have cyclopentadienyl ring and CO. So in presence of potassium, what will happen in presence of potassium? So this metal bond will cleave. Okay, this metal bond will cleave first of all. Okay, so you just check how many electron system it is. So iron
18
is what?
electron.
So you have to break this carbonyl and this bond. Now check what you are getting. So just look at one iron center. Suppose I am looking in this left side iron center. So what you are getting? So how to break the bond? You have to break like this. So you have cyclopentadienyl ring, then you have iron center. Okay, now if I look out only on this left side carbonyl, so what I am getting? You have two carbonyl attaching here, right? This bond breaks and this bond breaks, so that means if two bond breaks, so you will get two negative charge. Now see, so how many electron system it is? Sorry, not two negative, because this one is your bridging ligand, right? This one, this CO, this is a bridging ligand, so you will get only one negative charge because one sigma bond is there. This bond is not your covalent bond, this is the bridging ligand. So this bond is actually like this. CO is donating directly two electrons to this iron center, and this CO is donating electrons to this iron center, like this. Okay, fine. So basically if you break this bond, so you have one iron center, you have cyclopentadienyl, two CO groups you have, and you are breaking one sigma bond, so you will get one negative charge. So 5 electrons from cyclopentadienyl for iron center, how much electrons you will have?
18 electrons. Or 8 electrons.
8 electrons. For 2 carbonyl you will get 4 electrons
Plus 4. Plus 1.
plus 1. So 5 8 13, 4 17, 1 18 electron. Okay, so you have to make it 18 electron, like that you have to break. Fine.
Yes, sir.
So basically if you check the right side also, you will get the same thing. See, in the right side also you have iron center, one cyclopentadienyl, this
Carbonyl.
carbonyl, and this bond is breaking, so one negative. Okay,
Yes,
fine.
sir. Clear.
Okay, okay. Now next, suppose one question is like this, that which of the two, which of the two is which of the two is more stable? So what you have? So you have this manganese CO whole 5 minus negative charge, and another one you have this Mn2 CO whole 10. Tell me which one is more stable?
First one,
First one. Why?
it have a negative charge.
So what will happen if you have negative charge?
More back bonding.
More back bonding. So that is the thing. So if you have negative charge on metal center, it can back donate the electrons, and if it back donates the electrons, this metal carbon bond is becoming much more stable or much more strong. Okay, so this one is more stable. Okay. Why? So write down just here that better back bonding. Okay, better back bonding. Okay, so therefore this is what, this is your more stable compound. Better back bonding, so you are getting more stable compound. Okay.
Yes, sir.
And also we have know that if you have metal bond and metal ligand bond is actually more stable than your metal. Here you have metal ligand and here you have two manganese, so that means you have metal bond. Okay, fine. So these are the things. Okay, now write down next that reactions. Okay, just a minute, write down here that reactions of metal carbonylates, reactions of metal carbonylates. Okay. So suppose you have this OH minus, okay, you have this OCH3 minus, and then you have OET minus, and if you have ammonia. Okay, so this is oxygen containing, okay, these things. So they are acting as nucleophile. Okay, they can act as nucleophile as well as base. Okay, they can act as nucleophile as well as base. So suppose you have OH minus and you are treating this compound with methyl iodide CH3I. So that time what will happen? That time OH minus will attack from the back side and you will get methanol as your product. Okay, as your product. And suppose I have acetic acid CH3CO2H. So that time OH minus will abstract the proton from here, and what you will get? You will get CH3CO2 minus plus water. So here it is acting as your nucleophile, but here it is acting as a base. So they can act as both base and nucleophile as well. Okay.
Yes, sir.
So these metal carbonylates, if you have some metal carbonylates in general, suppose you have metal CO whole X and negative charge. So this kind of metal carbonylates, they can also act as nucleophile, okay, as well as base. Okay, so relate with your organic chemistry, it will be easy to understand. So if you have metal carbonylates, they can also act as a nucleophile as well as base. Okay,
Yes, sir.
fine, clear,
Yes, sir, clear.
clear, right? Okay, now suppose you have this, so manganese, then you have here CO whole 5 negative charge. Okay, so if I react with this methyl iodide CH3I, so what will happen? So think, this negative charge will attack on the carbon center, iodine will leave from here. Okay, so what I will get? I
Yes,
will
sir.
get this thing, CH3 group is there, then you have manganese and CO whole 5. So this is the compound you have. Okay, and if you react with H3O plus, so that means this negative charge will abstract a proton from here, and that time you will get this thing, hydrogen, manganese, CO whole 5. Okay, if you have water, water means what? Like this, na? So this negative charge will now abstract a proton, and that's it. So here it is acting as a base, and if you have carbon containing something, so that means it is acting as a nucleophile. Clear?
Yes, sir.
Clear?
Yes, sir, clear.
Fine. So now let's see some examples. So suppose here you have manganese CO whole 5 and it contains a negative charge. So write down the product. The two reactions we already have done, H3O plus, CH3I. These two reactions we have just done. Okay, write down. Now suppose apart from that you are reacting this compound with this R3SiCl, trialkyl silyl chloride. Okay, next suppose you have this allyl bromide. Okay, allyl bromide. Next suppose you have this Br2. Next you have this thing RCOCl acyl chloride. Okay, next you have CF3I. Okay, and suppose you have rhenium CO whole 5 Br. So tell me the product quickly. What will be the product? So this product you know, H3O plus. Here what you will get? Hydrogen, manganese, CO whole 5. Here if you react with methyl iodide,
CH3 manganese CO5.
CH3 manganese CO whole 5. Next,
R3SI
so
manganese
basically this
CO5.
negative charge will attack on the silicon center, chlorine will leave. Okay, it will attack on the silicon center, chlorine will leave from here. So I will get like this R3Si, then you will have manganese CO whole 5. Okay, here
Bromine will be with it will attack the carbon center.
so basically you will get like this. But if you see uh, so this thing manganese CO whole 5 negative charge, right? So how many
Yes, sir.
electron it has?
18 electrons.
18 electrons. So initially you will get this. Okay, here it is eta 1. Okay, here it is actually eta 1, but it will undergo further reactions. One of the carbonyl will leave from here,
Dissociative mechanism.
dissociative mechanism. So you will
Eta
get
3.
manganese, then what, CO whole 4. So here you are getting 16 electron, and then you will get what, manganese, CO whole 4, and yeah, here you will get 18 electron.
Yes, sir.
Okay.
Yes, sir.
Okay, if you have this reacting with bromine, so that time what you will get? You will get just bromine,
Bromine.
manganese, CO
CO
whole
whole 5.
5. This is the compound. Okay, if you react with this acyl chloride, so that time it will
It will
be
attack
R,
the carbon
uh,
center.
C double bond O, manganese, and this side you have CO whole 5. Okay, if you react with this CF3I,
Iodine will attack the carbon center.
so here now see, basically so you have already negative charge, okay, negative charge, okay. Now iodine is more electronegative, that we know, but fluorine is actually more electronegative than iodine, okay. So fluorine is getting delta negative charge and iodine is also delta positive charge, and this carbon center is also delta positive charge, okay. But fluorine is actually highly electronegative. So what happens here, due to high electronegativity of fluorines, the bond actually breaks like this. The bond is not breaks like this. Generally, if you have not fluorine, if you have CH3, that time the bond will break like this. Iodine will get the negative charge, carbon will get positive charge. But here, due to high electronegativity of fluorine, the bond will break like this. Okay, so you have positive charge on iodine. So basically, now manganese minus is abstracting the iodine from here, and this bond breaks like this. Okay, so basically here the compound will be manganese CO whole 5 iodine.
Iodine.
Okay, if you see here, you do not have any fluorine, so that is normal. Negative charge will attack on the rhenium center, bromine will leave from here. So here you will get what you have, CO whole 5 manganese. Manganese is reacting with rhenium center, rhenium also have 5 carbonyls. Clear?
Yes, sir, clear.
Okay. Suppose you have this 2 Mn CO whole 5 negative charge, and I am reacting this with your this HgSO4 mercury sulfate, okay, in 1:2 molar ratio. So what will happen? Am I audible?
Yes, sir, audible.
So what will happen here? So here Hg is basically what? This is your 2 plus and SO4 2 minus, right? So mercury is actually reacting with one manganese side, because you have negative charge on manganese, manganese CO whole 5, so it will be manganese CO whole 5, and with this side in the left hand side also it will do the same kind of bond, manganese CO whole 5. Fine.
Yes, sir.
Similarly, uh, suppose you have this thing. So here you have tin and 3 chlorines are there. Okay. Okay. 3 chlorines are there, and this side I am reacting with 3 CO whole 4 minus. So this is your cobalt carbonylate, okay, compound. So what will happen? Basically if you have negative charge, so that means it is on the metal center, so that will attack. So this negative charge will attack on the tin center, and chlorine is a good leaving group, so it will leave from here. So basically what you will get, you will get a compound like this. You have benzene ring here, tin you have, and now it will add with CO whole 4, again you have CO, CO whole 4, again you have CO whole 4. Okay, 3 units we are using this, 3 moles we are using this, so one by one they will attack and chlorine will leave. Okay, clear?
Yes.
Okay, suppose you have this chromium CO whole 5 and 2 minus. Okay, now here I am reacting this thing with RCOCl. So what you will get? So initially you have two negative charge, so it will attack on the carbonyl carbon, it will break, it will come back, and ultimately chlorine is leaving. So out of this two negative, one negative is doing this, right? So what I am
Yes,
getting,
sir.
so you have chromium CO whole 5 is already there, so chromium is now making bond with carbon double bond O R. So with you have already two negative, out of this two negative one negative is making a bond, so one negative remains here. Now this negative, what it will do, it will do resonance. So if you show the resonance, you can see like this. Okay, so what I am getting, CO whole 5 chromium double bond carbon, oxygen is getting negative charge, and you have one alkyl group. Okay, now suppose you have this R3O plus and BF4 minus. So if you have this kind of agent, these are basically your alkylating agent. Okay, alkylating agent. So they can simply give you CH3I here. If they are giving CH3I, you can do it. But they will give like this R3O plus BF4 minus. So what will happen basically here? So see, oxygen you have, and you have three alkyl groups, right? And oxygen is actually positively charged, so this negative charge will attack on the alkyl group, and this oxygen will be neutralized. So if you have R3O plus BF4 minus, just keep in mind that one of the alkyl group will add with the negatively charged. Okay, so what will happen, CO whole 5, here you have chromium double bond carbon, this side you are getting OR, and here already you have R. In alkylating agent you can use various types of agents. Suppose you can use CH3I methyl iodide. Okay, you can use diazomethane CH2N2. Okay, you can use R2SO4 dimethyl sulfate, or you can use this kind of reagent also, R3O plus BF4 minus. Okay, all the reagents are possible, all the reagents are possible. Okay,
Yes, sir.
so you have this compound, and now I am reacting with this thing, Na2 Cr CO whole 5, 20 degree centigrade, THF is the solvent. Can you tell me what will be the product? Try to do it. Done. So what will happen now?
So sodium it will give it 2 electrons.
Hmm. So Na2 means what? You will get 2 sodium plus and this here CO whole 5. If I break this compound, what you will get? 2 sodium plus what? Chromium CO whole 5, 2 minus,
Mm.
right? So what will happen now? Out of this 2 minus, one negative charge will attack here and chlorine will leave, right?
Yes,
Suppose
sir.
here you have two negative charge, so one negative charge will attack here and chlorine will leave. That you have to show first. So if you show it, what I am getting? So this side you are getting chlorine, okay, and here you are getting chromium CO whole 5. So one negative charge react here but the other negative charge remains here. Now this negative charge will come back and chlorine will leave from here. So what I am getting? What I am getting? So here you have phenyl, here you have phenyl, next you have double bond, here chromium CO whole 5. So that is the compound you have, okay. Fine.
Yes, sir.
Okay. So now it is okay, this thing you have. So in presence of sodium mercury, what will happen? This metal bond will break, okay, because sodium donates electrons. So what I am getting here, you have cyclopentadienyl, you have metal CO, 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 and negative charge you will get here, okay. So 2 units of this you are getting. Now next, suppose I am reacting with this reacting with bromine. So what will happen? This negative charge will attack on bromine and this bromine will leave from here. So what I am getting? So you have one cyclopentadienyl, next you have metal, and this side you have bromine, and here you have what? 3 carbonyl, right?
Yes, sir.
If I give here lithium aluminum hydride, so that time what will happen? In presence of lithium aluminum hydride,
Bromine it will attack.
so H minus will attack on the metal center, bromine will leave. So basically you have cyclopentadienyl ring, you have metal center, hydrogen is there, and here you are getting 3 carbonyl, okay. Okay, if I react this intermediate with your acetic acid CH3COOH, so here actually it is acting as a nucleophile in this reaction, but if you react with some acid, so that time it will act as a base, okay. So M minus will abstract a proton from the acid, okay. M minus will abstract a proton from the acid and you will get this thing. Clear? Any doubt?
Yes, sir. No, sir. Clear.
Clear, right? Fine. So it is done. Next you have, suppose this Mn2 CO whole 10. I am reacting this with hydrogen, okay, in presence of 150 degrees centigrade and 200 bar. So what will happen? So you will get basically hydrogen Mn. First of all, this manganese bond will cleave, and if manganese bond is cleaving, so you will get this HMnCO whole 5, because this Mn to CO5, it is basically like this. You have manganese, now this side you have 5 CO bond, and this side also you have 5 carbonyl bond, like this. But this bond is cleaving when you are reacting with hydrogen. So one hydrogen you are attaching with this side, and one hydrogen with this side, so you are getting HMnCO whole 5. Okay. Similarly, suppose you have here rhodium, then you have ppH3 whole 3 CO. It is also adding with rhodium. Then you have ppH3 whole 3 CO. So in presence of hydrogen and 80 atmosphere pressure, what will happen? This metal bond will cleave. Okay, so you just attach one hydrogen to this side, one hydrogen to this side. So what I am getting? Hydrogen, rhodium. Okay, then you have ppH3 whole 3 CO. Clear?
Yes, sir.
Okay. Next, suppose you have this CO2 CO whole 8. If you add with hydrogen and heat, what you will get?
HCO CO4.
So that time you will get hydrogen, cobalt, then CO whole 4, 2 moles of this. Correct. Now, suppose you have this CO whole 4, manganese, iodine. This is your coordinate bond. Okay, so that means iodine is donating 2 electrons to the manganese center, but this is your covalent bond. Here manganese is donating 1 electron, iodine is also donating 1 electrons. Now here also this is your covalent bond and this is your coordinate bond. Okay, so if I react this compound with 2 moles of pyridine, okay, 2 moles of pyridine, so what will happen? So first of all you just see for this manganese center, for this metal center only. So manganese is what? How many electrons? In manganese you have 7 electrons. For 4 carbonyls you will have 8 electrons. For this
Yes, sir.
covalent bond you will get 1 electron. Per manganese center you will get 1 electron, and iodine is donating 2 electrons. So if you add all them, what you are getting? 17 or
18
18
electrons.
electron you are getting, right? So basically I have to, in presence of pyridine, I have to break this covalent bond. Okay, if you break this covalent bond, what you will get? So you are getting, see what you are getting, CO whole 4. Just see for one manganese center what you are getting. So manganese, okay, and this iodine is present there, right? This iodine is present, right? So just see for one manganese center what you are getting, CO whole 4 manganese iodine. So how many electrons you have? 8 electrons from this carbonyl, 7 electrons from manganese, 8 7 15. Okay, and so you have one iodine, one iodine is present here. Okay, fine.
16.
So basically what you will get, you have pyridine. So pyridine will donate the lone
2
pair
electrons.
to the manganese center. If pyridine donates the lone pair to the manganese center, that time you will get 18 electron. Okay, that time you will get 18 electron. Fine.
Yes, sir.
Okay, so we have few more reactions we have. Okay, let's see what we have. So next, write down that transition metal hydrides, transition metal hydrides. Okay, so what do you mean by transition metal hydride? So that definitely the metal should be the transition metal, and hydride means it is actually directly linked with hydrogen. Okay, so this kind of compound you have. Okay, transition metal hydrides. Okay, so the metal should be your transition metal, and metal is directly linked with your hydrogen, and this kind of compound is basically amphoteric in nature. Okay, now what do you mean by amphoteric? So amphoteric means they can release H plus as well as they can take up H plus. They also takes up H plus, they release H plus as well. Both the things is possible. Okay, uh, transition metal hydrides we will see. Suppose you have main group hydrides. So main group hydrides, I think you know already what are main group hydrides. So lithium aluminum hydride. So if I write down only the anion counterpart LH4 minus, so this is basically your main group hydride. Suppose you have sodium borohydride, I am writing only the anion counterpart BH4 minus. So these are basically what? These are basically your H minus donor. Okay, so now we are coming back to our transition metal hydride. So what they are actually asking, that if you have this kind of compound, suppose you have this manganese hydrogen, so what can happen? So basically this hydrogen can release as H plus or H minus. Okay, both is possible. Okay, both is possible. So like amphoteric solvent, the best example is your water. Okay, if H plus leaves from here, you will get OH minus. If it takes up one H plus, that time it will become H3O plus. So this is basically your best example for amphoteric. So here also the same thing is possible. Okay, same thing is possible. Okay, clear.
Yes, sir. Clear.
So basically we have to see, suppose you have carbonyl group, so carbonyl ligand you have. So carbonyl ligand is attaching with the metal center, so that means you have electron withdrawing group present. Okay, suppose I am writing another ligand, another compound like this, ammonia whole 5, then you have manganese hydrogen. So that time you have electron donating group or electron donating ligand is present attaching with the manganese with the metal center. So both is actually possible. Okay, so one example I am doing, suppose you have this example. Okay, you have cyclopentadiene. Okay, then you have your iron, uh, you have two carbonyl here and one hydrogen. Okay, so if you treat this compound with HCl, HCl means what? H plus Cl minus, right? So that
Yes, sir.
time what will happen? That time this hydrogen will actually release as H minus. Okay, this H minus will abstract this H plus and hydrogen gas is releasing, which is a thermodynamically favorable process. Okay, and if hydrogen is releasing as H minus, so which charge left on the metal center?
Positive
So
charge.
positive charge will be here. So positive charge is here. Okay, positive
Yes, sir.
charge is here. And what is the counterpart you have? Cl minus. So Cl minus will attack here. So Oh yeah, can you turn off the mic? Yeah. So you are getting this compound, iron Cl bond. Okay. Now suppose I have this. I have this compound, and I am reacting this with diazomethane CH2N2. So now in organic chemistry I have shown this diazomethane is actually existing like this, N2 plus and CH2 minus. So that time what will happen? This CH2 minus will take up the proton. Okay, CH2 minus will take up the proton, and this bond will break. So once this bond breaks, what we are getting? So negative charge, and here I have 2 carbonyl. Okay, next if this CH2 minus takes up the proton, so what I am getting? CH3 N2 plus, CH3 N2 plus. So this negative charge will attack on the carbon center, nitrogen will release from here. So what I am getting? So here you have Fe, this side you have methyl CH3, and here you have 2 carbonyl CO. Clear? And what gas is releasing from here? Nitrogen gas is releasing from here. Clear? Any doubt?
Not that clear.
Clear, right? Fine. Suppose you have this compound HCO whole 4. So see, if I show the bonding, so hydrogen, then you have cobalt. Okay, and I am showing one of the carbonyl. So carbonyl is basically like this, CO plus, right? So if you have carbonyl, what I told you, that this is basically your electron withdrawing group, right? So if you have electron withdrawing group, so that means basically what, this bond electrons, they are coming to the cobalt center, cobalt is donating the electrons to the carbonyl, pi star orbital of carbonyl, right? So this bond or this metal center is actually becoming what, electron deficient. So if you have electron withdrawing group, that time the hydrogen can release as your what, H plus, right? That is actually favorable. But suppose you have this kind of thing, hydrogen, then you have cobalt, okay, then you have CO whole 3, and next you have PPH3. Okay, PPH3 or chlorine, anything. So what is happening here? So hydrogen you have cobalt, okay, you have carbonyl also, and here you have PPH3. So PPH3 is basically sigma donor ligand. It is actually donating the electrons to the metal center. So basically electron density is increasing on the metal center. The electron density is increasing on the metal center, so that means the hydrogen is now also electron rich, so it can release as your H minus. Here the hydrogen can release as H plus. Both are possible. Okay, fine. Now this is one question. So suppose you have this. So in presence of heating, what we are getting? They have given hydrogen gas is releasing plus product A you are getting. So what is product A? They want to know. So you have only this compound in presence of heating. Hydrogen gas is releasing and you are getting one product A. So what is the product A? How can you find it out?
Positive charge of iron.
Positive charge of iron, yeah, but you have to do it, na. So yeah, suppose you have 2 moles of this, that time you can do it easily in presence of heating. What will happen? So H minus, suppose it is abstracting this proton. Okay, so that means what, this bond will break. So H minus is
Metal
acting,
metal
so
bond.
here you are getting iron plus and here you will get iron minus. So basically what will happen, iron iron
Metal
bond
metal bond.
formation. Okay, metal metal bond formation will be there. So yeah, you have Fe here, CO is there, CO is there. It is also attaching with another metal center, iron. Okay, so this is the compound you will get. Clear? Any doubt?
Copper. Yes.
Fine. Okay, so that's it for today. We have few more reactions. Okay, that will take I think half an hour. So that's what I am not continuing now. But yeah, in the next class we will start mechanisms of your organometallic chemistry, oxidative addition, and those things. Okay. First of
Okay.
all, we will complete the reactions, then we will start that. Okay. Any doubt from today's class?
No, sir.
No. Okay, so practice it well. Okay, revise the old things, old chapters, and yeah, study well. Okay.
Thank you, sir.
Okay, bye. Thank you.